Hi class, welcome back to the next section, chapter 12.3, polar coordinates. I'm going to remind you guys every so often that in this chapter, a lot of sections overlap a chapter that I have in my pre-calculus video series. Um, and since this is calculus 2, we breeze through some of these topics a little bit faster because it's assumed you've seen these. So if you need a more in-depth look at any of the sections we're going over in this chapter, highly likely that they will be in that pre-calculus course. Obviously, things like calculus on um, parametric curves is not going to be on there because it's a pre-calculus text, not a calculus text. So things like surface area and derivatives would not be in there. But I do talk about polar coordinates. I do talk about um, a lot of the sections that are coming up. In fact, one of the sections that are coming up is something like 3 videos on its own. So it gives you a chance to kind of look at things. At a deeper depth. So if you're kind of fuzzy on any of these topics, my suggestion is to go to the pre-calculus and take a look through some of the later sections over there. And a lot of times there's a lot of overlap, and we take a little bit more time going over those things. If you're completely comfortable with the material that we're going over, then that's fine. Okay, so let's go ahead and get started. Let's talk about polar coordinates. So we did talk about polar coordinates a little bit already, more so indirectly than anything. So now we're going to start focusing on them primarily. Okay. So polar coordinates is basically a type of parameterization that we're doing. The regular coordinate system that we're used to is the rectangular coordinate system, the one that we've been using so far. Also called the Cartesian coordinate system. So this is its proper name. This is more of like its common name, right? We always call it the rectangular coordinate system, but its proper name is the Cartesian coordinate system. So this is the standard way that we plot points and functions on a graph, right? We look at x and we look at y, and we have our 2 different axes, right? However, there's numerous other ways of plotting points and functions on a graph. Things like polar coordinates, which we're going to go over in this section, the um, cylindrical coordinates, spherical coordinates, the parametric equations that we've gone over already, and vector equations, just to name a few. So there's different ways of sort of um, having the same kind of object and talking about them differently, but them being identical, right? So that's um, typically what we call isomorphism, right? So it's the same thing, but it looks differently in 2 different systems, and so then there's a relationship that we can have between them, those systems, right? Our objects. So in this chapter, we're going to be looking at polar coordinates, right? So we've talked about the parametric equations, um, parametric curves. So now we're going to move into a specific type of those, which is polar coordinates, right? So instead of using x, y to get to a point on a graph, in polar coordinates, what we do is we talk about a radius and an angle. Okay, so I talk about how far out do I have to go, and what's the angle I have to sweep from there to get to a similar point by using x, y, right? So normally, if we had a point x, y, okay, we move over a certain amount x, and then from there, we move up a certain amount, which we call y. Okay. Now, polar coordinates, what we do is we move out a certain radius length. Okay. And then from that radius length, we sweep a curve until we get to the exact same point, right? So this is our radius r, and we just move it like an arc on a circle by a certain degree, which we call theta, and that gets us to the exact same point. So instead of going, you know, like through a downtown city blocks and going, over a certain number of units and up or down a certain number of units, we're going to move out a certain number of units, and then we are going to rotate by an angle to get to that same point. Okay. So our coordinates in polar coordinates can be interchanged, where they're written as r and theta. So instead of x and y, we talk about the radius and then the angle that we sweep. And we can relate our rectangular coordinates and our um, polar coordinates by using some equations and formulas to go back and forth between them, right? So my xy point goes and turns into a r theta point. It's the same point, it's just how I get there is different. So r is the same thing as x squared plus y squared square root. And we get that from the triangle that we have here, right? This radius of a right triangle. And so this radius, we know r squared is x squared plus y squared. So if I want just r, I square root both sides of that, and I end up with um, r is square root x squared plus y squared. I want to get the angle, so I'm going to use the tan inverse of y over x because I will know my x and y, right? And so in order to find this angle, knowing only x and y, let's say, that's the only thing I have, I would need, that's a tangent, okay? And so the reason that our function uses a tangent, not a cosine or a sine or something like that, is because I should be able to find theta whether I know r or not. Okay, so if I'm only given a values x and y, I need to be able to use these values to find r or to find theta. I shouldn't use these values to find a new point and then use that with one of these to find theta. So for instance, if I was going to do um, cosine inverse, right? I know x and y. So let's say I'm like, okay, let's go um, x and r. Well, r isn't one of the original things I was given, right? So if I use x and r to find theta, I'm now assuming that this r is correct, right? And so we never want to assume that our math is correct. We want to use the original objects that we have. So I'm given x and y. How do I use x and y to find theta? I would use tangent, right? That's a tan inverse. So that's why we use um, r is based on x and y, and our theta is also based on x and y. Okay. So if I want to go the opposite direction, instead of going from rectangular points to polar points, let's say I start in polar points and I want to go back into the one that I'm used to, x's and y's. It's very, very similar. Okay. Again, using that triangle, we know x is r times cosine and y is r times sine theta. So once I have x and y, that's it. And again, looking at this triangle that I have, okay, hypotenuse of r, x, and y. And so we know from trigonometry, right, on the unit circle, it would just be x and y. But if I have a radius of r, that x and y gets multiplied by that radius that I have. So um, x, remember, is cosine, y is the same as sine. And so if we have a circle radius r, which we're using, it's r cosine and r sine for changing back into rectangular, given that I already know r and theta, right? So for both of these to find x, I'm using r and theta. In order to find y, I'm using what I already am given, r and theta. Okay. One thing to watch out for is that polar coordinates are not unique. Okay, what does that mean? It means that I can represent a point in polar coordinates using an infinite number of different values. Okay, I can always change things and end up in the same point. When I'm looking at a point x and y, let's say the point 1, 2, there's no other way for me to talk about that point 1, 2 besides 1, 2. However, if I'm talking about polar coordinates and I want to sweep out a radius and then um, curl an angle in order to get to the 1, 2 value in rectangular coordinates, there's lots of ways for me to do that. I can do a negative radius, right? I can go in a negative direction for my angle that I sweep. I can completely pass that point and come back to it and still end up there. And so now my angle is larger than 2 pi, right? So there's lots of ways to represent the same point in polar coordinates, but there's only one way to represent a point in rectangular coordinates. Okay? So let's do some examples. So let's say I want to express point 3, negative 3 root 3 in polar coordinates four different ways. So this is an x and y. How do I know? Because this is a number and this is a number. It's not an angle, right? It's not saying it's this many radians. If there's a pi here, I could assume that it was in polar coordinates, but it's always going to tell you um, what it wants you to do, right? So it's very obvious that this is not an angle, right? My radius is the first term squared plus the second term squared, right? So what we're going to do is we're just going to represent this into polar coordinates in the first place, right? So I'm going to go from x, y. I'm going to go to the easiest form, which is just following this formula. What's the radius I need and what's the angle I need in order to get to um, this point 3, negative 3 root 3. So for the radius, okay, square the first term, square the second term, add them, take the square root, right? So this is going to be 9, and then this is going to be 9 times 3, right? And so 9 plus 27 is 36. Square root of 36 is 6. So this has a radius of 6, and the angle is y over x. So with 3 root 3, here the 3's cancel, okay? And it's root 3 over 1, okay? Negative. And so for that, I can rewrite this as root 3 and the 1 separately being over 2, okay? This now lines up more with what I need for a unit circle, right? Or really not even need a circle, any circle, right? So the tangent here, this is, if this is wide, this is the large side. So this looks like it would come from a 60, 30, or 30, 60, 90 triangle, where this is the 60-degree mark, right? So we have pi over 3, but it's negative. So that's negative pi over 3. So that's basically a negative 60 degrees, okay? So this point is in quadrant 4 because I know I have to go out 3 and then go a negative 60 degrees, negative pi over 3. And so that leaves me in the fourth quadrant. Okay. And so anytime now, I just got to make sure that's where I end up. Okay. So it's good to know this. So my theta is negative pi over 3 and my radius is 6. So as polar coordinates, I can write this as 6, 5 pi over 3. Here I'm just equating what this is, right? Negative pi over 3 is the same as 5 pi over 3, so I'm going to write it as 6, 5 pi over 3. So that's one form, right? So that means I go out 6 and I go in a big circle all the way until I end at that spot in the fourth quadrant. The next easiest form to do is just to go 6, negative pi over 3. So going out 6 and then going down 60 degrees instead of coming out and coming around 300 degrees, right? 360. So minus 60, I would come around 300. So that's two ways of doing it, right? Those are the two easiest ways right there, right? Moving one way in the circle and moving the other way in the circle. Lots of other ways. So what's another thing that I can do? Let's use a negative, okay? A negative uh, radius, meaning that I move into negative 6 and then I go whatever pi minus 3 is, right, for the angle that I move, which would be 2 pi over 3. So I start at the ordinate, I move backwards 6 units, and then I sweep down from there an angle of 2 pi over 3. Okay. And I will end up at the same point. So negative 6, 2 pi over 3. For the next one, let's go ahead and just play with the negative angle again. So for this one, for the last one, I went negative and I went in one direction. For the next one, I'll go negative and I'll go around the circle in the other way. Okay. So here, I'm going to go pi, I'm at pi, and I'm going to go plus pi over 3. Um, so that's going to be a full half circle and then one more. Okay. And so in the negative direction, right? So I'm going backwards. So from negative 6, I go one full pi and then a pi over 3. Right? A pi and then a pi over 3 in the negative direction. And that's the fourth one. So as I said, I could go positive and then circle around like 10 times and land on my spot. And that's an equivalent way to do that as well. So there's an infinite way for me to represent these. These are the four easiest. Okay. With a positive radius, moving around the circle in either direction, and then with a negative radius going around the circle in either direction. Just make sure you're going around enough to land on the spot you want to. Okay? And so that's how polar coordinates work and their sort of flexibility that we have with them. Okay? Next example. So find the rectangular coordinates for the polar coordinate 2, 7 pi over 6. So it's telling us it's in polar, and we want to find the rectangular form. Notice it's not saying find four different ways because there's only one form here, right? So there's only one point in the rectangular form, the Cartesian form. So that's all we'll do. So remember, we have several, okay, we're in this case, we're given polar and we want to change the x and y. So we're going to use the r cosine and the r sine, right? Very, very easy to do. Okay, so x is r cosine theta. Okay, so plugging in the values, I know that r is 2, my angle is 7 pi over 6. So this is basically 1 pi over 6 past pi, right? So I go to 180 and then I move another pi over 6, so 7 pi over 6. And remember, if pi over 3 is 60, then pi over 6 is 30. So I'm going 180 plus another 30, so that's 210 degrees. Although we just have to put in the value for this, right? So it's cosine, so it's negative, and it's for a 30 degree. That means that this should be negative root 3 over 2. Okay, so 2 cosine 7 pi over 6. So that's 2 times negative root 3 over 2. So the 2's cancel, and I'm left with negative root 3. Same thing for y. Okay, so the y value there is then it's a negative negative, right? It's in quadrant 3. So sine theta here should be negative 1/2, right? So I'm going to have 2 times negative 1/2, and that's going to give me negative 1. Okay, if you're fuzzy on this, go ahead and look up a unit circle, right? So um, ideally, you should be pretty strong with your unit circle and be able to figure the points out. But if not, go ahead and go find one and use one because for polar coordinates, we're all over these sine and cosine values, right? So um, if if you're fuzzy with your unit circle, maybe just have one handy for you to make these calculations go a lot easier, a lot faster. So my rectangular point is an x of negative root 3 and a y value of negative 1, okay, for this polar coordinate. We can also represent functions in polar coordinates, not just points, right? So if I have an equation in rectangular coordinates, I can have a polar form for that equation as well, just like we did for the parameterizations, right? Because basically what I'm doing is I'm taking x and y, and they're being parameterized with r cosine theta, r sine theta, right? That is how, um, that's our parameterizations for the curve. And so we can find these points. We can also um, translate equations. There you go. So we call these polar equations. Okay, so the polar form is the polar equation. In polar equations, my dependent variable is r, just like y is for the Cartesian. And instead of x as the independent, it's theta, right? So r depends on theta. As the angle changes, my radius changes as well. Okay, so let's do an example. So let's convert y equals x squared into a polar equation. So y is r sine, x is r cosine. My x is squared, so I'm going to have r sine theta is r squared cosine squared theta. Um, let's go ahead and try to get all my r's together because remember, r is my dependent variable and theta is the independent. So I want r equals some function of theta. So my goal is to isolate r outside of the function by itself and have r equals all the theta stuff left over. Okay, so I'm going to divide both sides here by r. Okay, it's a nice little trick. And then now I can divide both sides by cosine squared theta. So now I have r is sine theta over cosine squared theta. So 1 sine cosine is a tangent, and then I have a 1 over cosine, which is secant. And so r is tan theta, secant theta. If I were to graph this in, let's say, Desmos, I will get out y equals x squared. I will get a standard parabola, non-shifted parabola. Okay. Um, let's do that actually. And magically, we're here in Desmos. So let's go ahead and type this up. So r equals tan theta, secant theta. There we go. Parabola. we're not sure, we can always go y equals x squared. And you can see here that they overlap exactly. Okay, so if I were to turn one off, okay, they're both there. Okay, and we're back. So let's go ahead and look at another example. Um, so write the polar equation r equals 2 over 1 minus 2 cosine theta as an equation in rectangular coordinates. Okay, so here I want to just kind of get everything in line. I don't have to, but it's a little bit easier if I can equate this to a constant or just kind of not have a rational to deal with. So I'll multiply both sides by 1 minus 2 cosine theta. Then I want to start making my changes if I can. So first things first, let's go ahead and distribute this r through. Okay, and so now I have r minus 2r cosine theta. And notice here, this is a r cosine theta. That's exactly what I use for x. For r, I have a relationship for r squared. And so I use that form, right? The square root of x squared plus y squared. So I can make those substitutions into here. And now I'm into rectangular coordinates. However, we typically don't stop here. We try to free the, we try not to have any square roots. That's the easier way to think about it. Try to get rid of all square roots when you start writing things into the rectangular coordinates. So here, I will move my 2x to both sides. So I'm going to isolate this root. And then I am going to square both sides. So now I have x squared plus y squared equals 4 times x plus 1 squared. From here, I could multiply this out, expand this, and then kind of move everything over, and that's fine as an answer. This is also fine as an answer. Once I have my x squared and y squared kind of no longer trapped, we're okay with this as a form. So in the next couple sections, we're going to talk about um, some special geometric figures, and they're all represented by this x squared and y squared term. So that's the real reason why I want to get this out. Um, we do have standard forms for those geometric forms, and I talk about that more in the pre-calculus section than here. We don't really talk about it here. It's used, but it's not the goal of our course. Um, but it's easy to put this into that standard form for a conic, basically, is what we're going to be talking about soon. Um, and so I could expand this out and put it in, but this is fine as well, because then I kind of understand I have x squared plus y squared equals a multiple of something else squared, right? It's kind of in the form of a circle, right? And then even 4 is a 2, right? So now I have that my circle kind of changes based on a radius, right? Which also changes with the x here. So this is kind of okay for me at this point. So all of that to basically say, just make sure you get rid of the square roots over x squares and y squares if it shows up there. Okay. Let's talk about how to graph these things. Okay, not these ones, but the polar forms, right? This section is about polar equations. So um, one thing is how to find points for these equations, right? And what they look like on a graph. And then if I'm given a function, right, I want to be able to relate that function to something I'm used to already. And so then the last part is now that I know how to go back and forth between the two kind of coordinate systems, what do these graphs look like, right? Because we're talking about a whole different space now. And so the graphs, remember, are based on a radius and an angle. So even our graphs look different. And what I mean by that, I mean by the axis with which we graph things. We're no longer graphing x's and y's. We're graphing r's and thetas, right? And an angle always comes with a circle, right? So in order to graph these, my function r that depends on theta, we're going to make a table of values and plug in various values of theta, right? So like when you learn how to graph in regular XY coordinates, you pick a bunch of points, you plug them into your function, you see what you get out, and then you graph those points. That's basically what we're going to do in order to graph these, right? It's not super intuitive yet how these things work. We haven't even seen an example really. Um, so in order to graph these, what we want to do is we want to pick a series of points, angles, right? Because my independent variable here is angles, and then it will tell me the radius I have to get out when I'm at that angle, okay? And so we just want to pick a bunch of points. And so the points that we pick are the standard points that we use for a unit circle because it's easy to talk about cosines and sines of unit circle standard angles, right? 30, 60, 90, 45s, and all the other 90 degrees. So that's what we use when we look at these, okay? Um, Sometimes our graphs are going to repeat themselves after a certain angle value, so we really want to cut off our angle value, our range of angles, so that we're not repeating ourselves throughout a circle or throughout our graph, okay? Um, We can also, towards the end of this, we'll talk about the symmetries that are inherent in these kind of graphs and how to graph things maybe a little bit faster based on their form and based on the symmetries that are available to us. Okay, so let's go ahead and do an example. So this is just be a very, very standard example where we're just finding a bunch of points. Okay, so let's graph r equals 3 cosine 2 theta. If we just kind of look at this, this looks like r equals 3 cosine theta, right? But we have a 2 theta here. And we know that when we have a multiple of cosine, this is something like an x, right? This, if I had to change this back into coordinates, it would look something like this is almost an x value, right? Except for this r is over here. So I'm going to pick a bunch of values for theta. And for all of these angles, I'm just going to plug in, I'm going to find out my r. And then all of these points go together. So I'm going to look at 0, and I'm going to say that the output is 3, right? At the angle of 0. At the angle of pi over 4, I have an output of 0, and so forth. And so I'm just picking the standard, right? This is going through quadrant 1 and quadrant 2. And so I'm basically going 0 degrees, 30, 45, 60, 90, and then the next round of that also. And so notice that we do kind of have some symmetries that we can see already, right? We have 3, 3 halves, 0. Then we're going, so the positive, going down into negatives, going back up to positives. Look at my 0 is always centered around a 3 halves and a negative 3 halves, right? 0, negative 3 halves and a positive 3 halves. The 3 is also here. So even just looking at these outputs that are showing up, we can start to see a pattern, okay, which is nice. Patterns are always good. And then if I'm going through the bottom half of the circle through quadrant 3 and 4, you can see that that pattern kind of does it again. It kind of looks like a sine wave, right, or a cosine wave. And so, well, it is a cosine wave. But you can see how as I'm going through the angles, I'm going down and then back up in value, right? So here I was up in value and I'm starting to come down to 0. I'm going down to -3. I'm going back up to 0, up to 3, and then back down to 0, back down to -3, back up to 0, and ending at 3. So when I graph it, it's going to look like this. Okay. So remember, my angle is moving in directions this way. Okay. And so I started here at 0 angle, and I had an output of 3. And so as I move, I'm moving this way around my curve. Okay. Moving this way. Actually, it's very possible it doesn't move this way at all. Let's see what we have here. So if I'm starting at the previous value, pi, with a positive 3. So at pi, I have a radius of 3. And yeah, as I go through this, I have a positive value of 3 halves for my radius. Okay. I'm back down to 0. Yeah, so it looks like we're going this way, a lot around this clover. Okay. Very nice looking graph. So in polar coordinates, the graph is actually made of concentric circles, meaning that they're all circular, right? It's basically 4 circles that are moved and shifted in some way. Okay. So circles lying within each other of different radii. Okay. And the origin in rectangular coordinates, okay, is referred to as the pole in polar coordinates. You could think like if you're looking down on the ground, okay, there would be a pole kind of sticking straight up at you, and that's the pole that everything revolves around. Okay, so again, if you're looking down and all you can see is this little black dot here because you're looking down straight through a pole from its top to its bottom, right? So that's how I kind of like to think of the pole. And so that is the same thing as the origin in rectangular coordinates. The polar axis is the same as the x-axis, right? Because it tells me how far out I need to go for my radii, right? So we call it the polar axis because it talks about how one of the poles reach out, which is the radius. Um, so the same thing at x-axis, and it gives different values of r. So the polar axis is the x-axis or the r-axis, you could think of it as. And so we talk about this in terms of circles. We talk about how much out I have to go, and then I go through my circle. So typically when we graph polar coordinates, this is the standard form of the graph. It doesn't make sense for me to talk about moving up and over certain amounts if my entire system is talking about how much do I go out at whatever angle, right? So at this angle, I have to go out a radius of this much. So it's much, much more easier to graph something on a standard graph for polar coordinates. In fact, Desmos even has that for us. Okay, let's take a trip to Desmos real fast. So let's use the last function we had, 3 cosine 2, oh, use the backslash, 2 theta. Okay, and zoom in on this if we need to. If you come up here, so you can see here, we can talk about what angle we want to go through. So here we went through the full circle. I could change this to just pi, right? So this is kind of uh, what this went through. And let's say that we put a max of 4 pi and just do 0. Okay, so this is what we trace as we go through. And so uh, I put on 4 pi because as we draw this arc, okay, we connect here at 2 pi. You don't see anything because we're going around a second time, right? And so it makes more sense for me to stop this at 2 pi, but I just wanted to show you that that's the way that this works. So we can make this go in one direction only. Oh, what happened? Oh, looks like I broke it. There we go. So 2 pi. Let's just count this from 0. Let's see what we got. Okay. So as this goes, so I thought we are just going around as we went. Obviously, I was wrong. And so this is the path that we traced through as we go through this. Now, the whole reason I went to Desmos was not just to show you this, right? This is kind of happened, but they have a polar grid, and it makes much more sense to look at things in terms of this, right? So you can see here, everything that starts at a radius at 3, right? And so on this circle, you can see that we are at 3. Okay, for everything. So we cannot do both at the same time, okay? But you can see that it is the same graph, just it makes uh, more options. So this is in radians. We can change this to degrees if we wanted to. Oh, I guess actually we can't, 'cause it's in half pi in my formula. Okay, so we always do this in radians. And that's the way this works. And so we're back. So this is the standard graph that we use for graphing polar coordinates, right? So now let's talk about our symmetries. Cosine and sine, we know has inherent symmetries already. Okay, and whenever we're dealing with angles, we have symmetry. So if r equals a function is the same as if I were to plug in the negative angle and get out the same exact function, then I'm symmetric about the polar axis. Okay, so remember the polar axis is the x-axis, right? So it's just like flipping a regular graph over the x-axis. So something like this, right? My line of symmetry is the standard x-axis. What I have on top of that is the same as what I have on the bottom. If I make my whole function negative and I get out my regular function, then I'll be symmetric about the pole. Okay? Another way of thinking about that is that if I shift out my angles by pi, by looking at what's happening on the other side, if I get my same function, then I'm symmetric about the pole, which is the same thing as being symmetric about the origin, meaning that if I flip over the x-axis and then the y-axis, I'll get the same picture. So there has to be two flips, right? So if I flipped just this part down across the X and then across the Y, I get the same picture I had before. So this is symmetric about the origin. So for whatever function this actually is, if I had the whole function and then I turned it negative, it wouldn't change the values of my function. I would get the same values out. Another way of dealing with that, since I'm on the circle, if I plugged in something here, okay, and then I move 180 degrees, boom, I'm gonna get out the same value from my function. Okay, so that is for two. And so for the third one is that if I look at the angle I'm at and then I go backwards by pi, I'm gonna come out with the same value. Okay, and we say that that's symmetric about the y-axis, which is pi over 2, right? That's the 90 degrees, the y-axis. So that would be something like this. Okay. So if I were to take this graph and flip it across, turn it this way, I'd end up with the exact same thing. Okay. So those are our three symmetries, just like with rectangular coordinates when we have symmetries there, even odd functions, things like that. So let's look at some common forms of polar curves and how we can kind of guess what our functions should look like by just looking at the form of the equation. So the first is circles and spirals. If my radius is constant, right, then that means I have a constant radius. So a radius of 5 would just give me a circle of radius 5. I have a constant radius, right? If my function looks like r equals a sine theta, so again, remember this looks like me multiplying something times y. Well, look, everything is positive, right? It's positive y. It's symmetric across the y-axis. That kind of makes sense here. Then I get a circle, a circular figure, a spiral that is always positive in value for the output and is symmetric against the y-axis. Similar thing for cosine, a times cosine, which we just saw, right? Well, it was a little different actually. But here I'm kind of centered on the positive values for x, right? This is the positive values of x, which makes sense here. And so I have a sort of circular spirally figure that's symmetric against the polar axis or the x-axis. Okay? And then here I can get a spiral if my radius changes as my angle changes, right? So if I'll start off with a small and it'll just get bigger and bigger as I go out because as I'm changing, my radius is changing as well. Limousin. So here, if my function has the form r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta. So again, you'll notice that if we have something that has a cosine in it, it's kind of angled to the left or the right. If I have something with a sine in it, it'll be kind of more centered along the up or down, right? The y-axis for sines, um, x-axis for cosines. So along the polar axis and along the line pi equals 2, the angle pi equals 2, or pi over 2, I'm sorry. So my orientation depends on whether the function is sine or cosine and the sign of b, right? So a negative here, right, will have me, instead of facing up, facing down, right? Because I'll have a minus in here instead of a plus, so all the y values will be negative in value. So if my b is larger than a, I will have something that looks like this, okay? So here, this is very obvious that it is a cosine type function, okay? And if my b is larger than a, then I'll get this extra little twist on the inside. Here, if the outside value a is larger than b, there will be no little twist here. Here you can tell that this is a sine style function. So this is a plus some b sine theta, right? This would have been a plus some b cosine theta because I'm on the positive form in the x direction, positive form in the y direction. Something like this would also be positive, right? So this would be a equals b. So again, it very much follows these kinds of deals, right? But the relationship between A and B talks about what's happening on the inside of the curve here. Okay? So A equals B has this, this kind of like a peach, I guess. This one looks flat, and then this one has a full circle. So next we'll talk about roses. If our polar function has the form r equals a cosine n theta, so I'm multiplying my angle by something, which we actually saw, right? The first one that we graphed was 3 cosine 2 theta, or let's say I have a sine n theta. Instead, it's going to be an n-leafed rows if n is odd, or we call it a 2 times n leaf if it's even. So here, this is 3 theta, so it's going to give me 3 leaves. So this is a 3-leaved rows for sine, okay? Here, this is a 3-leaved rows for cosine, right? So remember when we had cosine 2 theta, we actually had 4, so we had 4-leafed rows. So here for a cosine 4 theta, I'm going to have an 8-leaf rows. So 2 times whatever the n value is. Okay? And here, I'm going to have an 8-leaf rows in sine. Okay. Next, let's talk about lemniscates. Okay, so this is a figure 8 shaped curve. So something of the form a squared sine squared and then 2 theta is going to have something like this. So if I change the values of thetas, I'll have different numbers of leaves in here. Okay. But here you can see I'm symmetric about the origin. Okay. Here, this is also symmetric about the origin. Okay. Or the pole. Sorry. And so here this would be a squared cosine squared 2 theta. And that's it. That's all we have today. So I'll see you guys in the next section where we start to talk about polar calculus on polar curves, I believe. Okay. Polar equations.